Welcome to Calculus 1, Math 2413 at Brookhaven College. My name is Professor Michael Bailey, and I'm going to be your instructor for this course. And so first, let's talk about calculus, which scares a lot of people. Calculus is actually quite simply the study of change, and specifically two ideas in relation to change. We're looking at instantaneous change and we're looking at accumulated change. Okay. Now, in the world we live in the times we live in, things like instantaneous change and accumulated change are relatively simple concepts that we understand. For example, if we are driving our car and we want to know how fast we're going, which is a rate of change, miles per hour. It's the change in distance over time. We simply look down at the speedometer and we can tell what our instant rate of change is. But think about it. A couple hundred years ago, sorry about that, a couple hundred years ago, when we were driving a horse and buggy, we didn't have an odometer or speedometer. So as we're going along, we don't really know exactly how fast or what our instant rate of change is or the speed of our horse. Okay, we might have been able to calculate the average speed, right? If we knew that the next town was 20 miles away and it took us 2 hours to get there, then we were averaging about 10 miles per hour doing a simple calculation, an average speed. But the instant speed or an instant change was a difficult concept to figure out without tools or technology. And then we also have accumulated change. In the example of the horse or you're driving, the accumulated change, remember we're talking about the change in distance over time. So our accumulated change is how far do we go? If we were going 50 miles per hour, our speed or our rate of change, and we drove for 3 hours, then totally we accumulated 150 miles. 3 hours times 50 miles per hour is 150. In calculus, we're going to be looking at both of these concepts, and we have a tool for each of these. When we're trying to figure out instantaneous change, we use a derivative. And when we're looking at accumulated change, we use an integral. And I call it math magic. Calculus has a lot of math magic. The original concepts of calculus were in the 16 or 1700s. And even then, it took another couple hundred years to see how some of the formulas actually made some of this calculation quite easy and worked in relatively miraculous ways. Okay, so let's move on. We've seen change before. Here we have a simple chart, and we can see pretty quickly that something is growing, right? So this is the Cartesian system. We have our y-axis going up and down. We have our x-axis going across, and we can see that the number of internet users is growing. And again, most of us know this intuitively from our experience with looking at graphs and tables. Now we can calculate the rate of change between these 2 years. We can calculate the average rate of change. And remember from algebra, this is the slope between 2 points. And I've drawn this line in here so you can see it. And remember that's the change in y's, delta y, over the changes in x, as we also call that the rise over the run. The rise, how far it goes up over the run. And here, if we have 2 point values, we can calculate it. And so using the point values here of 4 million and 1.5 million, and the x values is 1995 and 1990, we can see that our average change of internet users is 0.5 million internet users per year. Again, that's fine, but what if we wanted to know how the number of internet users was changing on a specific date, for example, March 5th, 1993. Again, what we're looking for is an instantaneous rate of change, and that's where the calculus comes in. I'm sorry about that popping up again and again, and I'm not even sure if you're seeing it. So let's look at this again from a different perspective. We're going to use limits to first figure out instantaneous change. So notice here we have a function, x squared minus x plus 2, And we're trying to figure out what happens exactly at 2. Okay, what's going on when we get near 2? Okay, and we're going to call this the limit as x goes to 2. So notice what we've done is we've started at 1, and we're calculating f of x, or the y value, at 1, and then we're getting closer to 2, so we're going to go to 1.5, and then to 1.8, and then to 1.9, then to 1.95. We're getting closer and closer. 1.99, we're pretty close, but we're going to even get closer. 1.995, 1.999, that's pretty damn close, right? So we can see as we come from a smaller to the larger number of 2, from 1 to 2, we're getting to 3.997. Let's see what happens from the other direction. So if we start at 3, f of x, by plugging in 3 squared minus 3 plus 2, that's what these values are, just plugging in our value of x and calculating. We start here at 8, and then we're getting, as we get closer and closer and closer to 2 by going to smaller numbers, notice, we get closer and closer to 4. We eventually get to this number, 4.003. So as we can see that what's happening as we're getting closer and closer to 2, the number's getting closer and closer to 4. And the way we would write this is we'd say the limit as x goes to 2 of x squared minus x plus 2 equals 4. Here's a graph of that function, and we can see that as we are approaching 2, that x is getting closer and closer to 4. And in this case, it actually is the actual functional value, and that's because this curve is what's called continuous, meaning that we could draw this whole curve without lifting our pencil off of the paper, and we're going to talk about that in a minute. So let's look at these kind of concepts of limits, okay? So we're going to look for the limit as x goes to a, some value of a here, okay? And so as x goes to a in the original, in this first graph, a, we can see that the limit would be that the limit as x goes to a of y is going to be equal to L. And that's just saying that the y value of this function in blue as x goes to a is equal to L. So we're saying, what is the y value when x is a? Here we have a continuous curve like the example we just looked at, so that's pretty straightforward. But what happens here, sorry about that, in B and C, because notice what we have here, it's maybe hard for you to see, but we have a hole. So when we get to A, all of a sudden our value for A, our functional value for A, is way down here. And in C, we don't have any value at all. If it's a discontinuous function, it doesn't exist at A. Okay? But notice what I want you to get out of this is that a limit isn't saying what is the value of the function at A. It's saying what is the value of the function when it is near A. So it doesn't even have to exist as we see in C, or it can be a totally different value as we see in B. But the limit as x goes to A for all three of these graphs, where it's continuous, where it's discontinuous with a jump, or where it's discontinuous with a hole, they all actually equal L, because as we get closer and closer to A, the y value goes to L. So it doesn't have to exist. It can have a jump here and still exist, etc. Okay? So that's the concept of the limit. Here's our notation. We say the limit as the value of x, or the input, goes to some constant, c, of f of x equals L. And we read this as the limit as x approaches c of f of x equals L. Okay? Again, if you imagine the graph, and this is a crazy graph, right? If you think of it as a road, and as you are driving, what value of L are you getting close to? What value of L, or what value of y, I should say, are you getting close to when you're getting close to the indicated x value? So let's look at something here. Notice if we're driving along the curve from the left of the graph and heading towards -4. So we start here and we're going to head up here towards x equals -4. We're getting close to the y value of, the y value here is -2. Okay, so we say the limit as x goes to -4 of f of x equals -2. Again, remember we're looking for y values. Y equals -2. This is just functional notation. Taking a little commercial break here, you'll notice that I started in chapter 1.3. You do have homework online for 1.1 and 1.2, which is really an algebraic review of functions and functional notation. I highly recommend you go online, do those homeworks. If you have any questions about it, go into the study plan and do the tutorial. Okay? All right, let's move on. Notice if we continue driving towards x equals -2, we're going to stay on this red curve and we're going to drive until x equals -2. All of a sudden we're getting close to a hole. Okay, there's the hole in the road. All right, but we're not looking for the actual value at x equals -2. We're looking for the value when x is near -2. Okay, so even though the actual functional value is off the road or off the chart, whatever you want to say, our limit is still the value of 3. So the limit as x goes to -2 of f of x equals 3. Okay, so we're looking at the main graph function and we're asking again, remember limits are about getting near to something. All right. We can also have something called one-sided limits, and what this is doing is it's telling us which direction to come from. So notice the notation here. It says limit as x goes to c, and then right after the c it looks like an exponent and it has a positive or it could have a negative, and this is telling us the direction to come from. So if we're think about a number line, if we're coming from the positive direction, we're going to be going from right to left. We're going to be heading in the negative direction, which is a little bit confusing, right? This is telling us where to come from. The limit as x approaches c from the positive direction of f of x equals L. The limit as x goes to c from the negative direction, again, think of a number line. If we're coming from the negative, that's what this is telling us, coming from, we would be going toward the right. Okay, so let's look at an example. Notice if we drive toward x equals -1 from the right or from the positive, when we get near x equals 1, y is equal to 4. Okay, so the limit as x goes to 1 from the positive direction of f of x equals 4. Notice if we do this from the other direction, we have to come way over here because we're coming to the negative direction. And as we go to 1 from the negative direction, again, this is telling us the direction to come from, f of x, or y, equals -3. Okay? And this is the one case where the limit, the whole limit, as x approaches 1, does not exist. And what we say here is that in order for a limit at a value to exist, it must have two one-sided limits which exist, and they must be the same. Okay, and so notice that this kind of makes intuitive sense again. Remember, we're talking about the limit as x goes to 1. What are the values of y when we get closer and closer to 1? Well, depending upon the direction we come, they're different. So there is no absolute limit as x goes to 1, because when we come from the positive it's 4, when we come from the negative it's -3. So we don't have an overall limit. So again, the limit as x goes to 1 overall, the full limit, does not exist. You'll see this notation through the course, DNE, and it just stands for does not exist. Okay, so remember this is very important for this first test and for this chapter. Full limits exist only if both one-sided limits exist and they are equal. Okay, and again, you see here about they're not the same. All right, let's look at some properties of limits. So these are some assumptions. We're saying that the limit of f of x equals L and the limit of g of x equals M. These should have a value underneath, but because we're just talking about general properties, you can assume that x goes to c. All right. So the first thing here just says that if we're taking the limit of a constant, it's always going to equal the constant. And you might think of this as y equals k or y equals 3. Well, that's a straight line across. So no matter what value of x I'm at, the value of y is always going to be equal to k, the constant, which is the formula. Here we have the limit of x as x goes to c is going to be c. Well, if y equals x, then every value of x is going to be equal to y, and this is just a diagonal line. Okay. Then we have the rule for sums and differences of limits. So if we take the limit of a sum, what we can do is add the sum of the limits. What does that mean? So what we can do is we can take the limit of each piece and then add them together here. Remember, the limit of f of x is L, and the limit of g of x is m. So if we have a sum here, we can add them. And this is just saying it works for sums or differences. So when we have a sum, when we're trying to take the limit of a sum, we can actually take the limit of each part and then add them. If we're taking the limit of a difference, we can do the same thing. Okay, that also works if we have a product. If we're taking the limit of a product, we can take the limit of each piece and then multiply them. It works the same with the quotient as long as the denominator is not 0, and that's all that's saying. Okay, and it also works the same with a radical or an exponential here. That if we're taking the limit of the nth root of f of x, this equals the nth root of the limit of f of x. All right. So now let's get to the concept of continuity. Okay, we say a function is continuous at x if you can draw the graph without removing your pencil, without lifting your pencil from the paper. Okay, so notice the function is continuous at x equals -4 because there's a dot there, but it's filled in, so that means it's part of the graph. So if we were drawing this graph, we could go right through that pencil and not have a problem. Okay. However, once we get up here to x equals -2, we actually have to lift our pencil off and move it up to this dot here at 5. When x equals -2, the function is f of 5. There's a hole here because the value is not on this line when it's near there. Okay. It's also discontinuous at 1. And it's also discontinuous at 4. When we get down here to x equals 1, we have to lift our pencil, fill this shade in, we have to lift it again to continue on. Then notice as we approach 4, we have an asymptote, x equals 4, and then on the other side, we have the other side of the asymptote. So we have to jump down here back to the top. Okay? When a function is continuous at x equals c, for example at -4, then the limit as x approaches c is the same value of the functional value. So all this is saying is the limit as x goes to -4 equals f of -4, which is the value we put into that formula. Okay, and that's what I'm saying here. So the limit as x goes to -4 of f of x equals -2, which we can see, which is the same as if we put the -4 into the original equation and solved. Okay. We can use this rule to calculate many limits in a simpler form, including most trigonometry, most rational functions, and all polynomials because they are continuous over all values of x. All right. Now you're in science calculus, and that means that we're going to have a much more precise definition of a limit. Now when we read this, it gets a little confusing, and then I'm going to show you a graph and help you see what it means. And this is really about constraints as well, and I'll explain that in just a second. Okay, so we get to our math terminology, and in this course we're going to have a lot of definitions. Let f be a function defined on some open interval. Okay, now remember an open interval is just saying between what two values of x does it go, and it's open means it doesn't include the endpoint. So we might say this is between x equals 0 and x equals 10. To document that, we'd have a left parenthesis 0, comma, 10, right parenthesis. It would also look like a point 0, 10, but it's not. Open interval notation often looks like an xy coordinate, so be careful with that in this course. Okay, so let f be a function on some open interval, some values of x, that contains the number a. So our value a is in that interval, except possibly at a itself. Okay. Then we say that the limit of f of x as x approaches a is equal to L. And so we write that as the limit as x approaches a of f of x equals L. So this is just saying in words what we've already said about this notation. This is true if for every number epsilon greater than 0, there is a corresponding number delta greater than 0, such that if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than epsilon. I know that's a mouthful, okay? And it's a little bit confusing with all these Greek letters in there involved as well, okay? So there's a couple of things what this is doing. All this is doing is giving you a range and saying that the limit exists and it equals L in some kind of range here, okay? So you might think about how strong a bridge needs to be or something. How strong does the metal need to be? And so we want the bridge, let's say the strength of the metal, to be in some kind of range here, okay? Now notice with the definition, you can tell what these variables are connected to. So notice that delta is an x value. Delta, this lower delta, is an x value. And I call this epsilon, but I don't even think that's epsilon. I think it might be mu or something. But this little e, this little Greek e, is a y value. You see it here, f of x. So this is a y value. Those are important to remember. And all this is saying is that in the region where, again, our L is our limit, our y value, notice our A here is the x value that we're heading towards. And so these epsilons represent a range around L. And so it's saying that the function value minus the limit value is less than epsilon. So it's all of these values in there. And here when we're talking about as x goes to A, x minus A is less than delta. And so this is just a range on each side of A plus or minus delta. Okay, so this little range here is delta, this is an epsilon, this is an epsilon. And so it's giving us kind of, we're trying to get more precise than just saying as it goes to A, because then we don't have, when we say the limit as x approaches A, well, let's say we're looking at the limit as x approaches 4. Well, if we're coming from 0, we could say x is 3 because we're getting closer to 4. So what this is doing is it's saying how close do we want to be to A in order to calculate this. So for example, if we made the delta 1/2, then the value I just said, the limit as x goes to 4, we wouldn't use the value of 3 because 3 would be out here. It's not within a half of 4. Okay, so these are giving ranges for how we would calculate the limit, or ranges we want that. You might look at error rates, etc. Okay, let me move on and show you a problem, and maybe this will help explain it a little bit more. So I've just taken elements out of the definition and put it here in orange. This is the precise definition. Again, you're probably an engineering student or a science student, so precision is important. And we're going to just prove that the limit as x goes to 3 of 4x minus 5 equals 7. Okay? Well, this is a polynomial. It's continuous at all functions. We could just plug it in, but it's asking for a proof. And when you're asking to do a proof, what you're doing is you're using a mathematical identity or definition to show that something is actually true. Okay? Now remember from our definition that our A value is wherever the limit's going to, so A equals 3, or the value of L is what the limit equals, right? The limit of f of x equals L, the limit of f of x equals 7, so L equals 7. So we need to find a number. To prove this, we need to find a number, delta, such that all I'm doing now is plugging in the values from this formula. All right, 0 is less than the absolute value of x minus A, x minus 3. And remember, these are, why are these in absolute values? Because they're distances. They're ranges around the A and the L, okay? And we always measure distances in positive numbers. I don't say I drove negative 150 miles to Austin. So 0 is less than x minus A, remember A is 3, which is less than delta. Then f of x, which is our formula, 4x minus 5, minus L, this is just directly from the definition, is less than epsilon. All right? So we've got to find some kind of delta figure that makes sense. All right? So notice over here that if we actually simplify this, we get 4x minus 5 minus 7, which is equal to 4x minus 12. Right? All I've done is drop the parenthesis, and minus 5 and minus 7 is negative 12. Well, notice there's a common factor in here, 4. If I factor that out, I get 4 times the quantity of x minus 3, which I can pull the 4 outside of the absolute value because it's a positive number and a constant. And so I get 4 times the quantity of x minus 3. Now, why do I want to know that? Okay. Well, notice that if I rewrite this original equation, it may make me see a pattern or a connection. So instead of writing 4x minus 5 minus 7, all I've done here is substitute in our simplified calculation of this, arithmetic of this. So if 0 is less than x minus 3 is less than delta, then 4 times the quantity of x minus 3 is less than epsilon. And again, that's just a simplification there. So what we're saying is, since 4 times the absolute value is less than epsilon, then I can rewrite this by dividing both sides of the inequality by 4, and I get x minus 3 is less than epsilon over 4. Notice this is the same format as here. We know that the absolute value of x minus 3 is less than delta, and that's what we're trying to find, is some value of delta. So notice if we plug this in for delta, epsilon over 4 is equal to delta, then we get 4 times the quantity of x minus 3, plugging this in here, I should have left this here and done this out first. 0 is less than x minus 3 is less than delta, right? But delta equals epsilon over 4, so if I put epsilon over 4 here and then times both sides by that, I get 4 times the absolute value of x minus 3. And notice if I do this out, then I get back to the original equation. So I get that if I put this inside, I get 4x minus 12, and then I can do 4x minus 5, which is our original f of x, minus 7. And so what we're doing here is we're actually working exactly backwards, 4x minus 12, and then taking out the 5 so that it's the actual function, and I get back to where I started, which is kind of circular, but that is actually what we do with the proof. All right, I think that's enough for you to get started with 1.3. Try the homeworks. Remember, there's homework in WebAssign. In the personal study plan, there's a tutorial for this section. There's a practice quiz for this section. And then also remember, where did I put that? I think it's in your syllabus. There's a list of problems that you should do, or practice problems in the back of each chapter and section. So calculus is a tough subject. It needs lots of practice. Do not just do the homework on WebAssign and think you're good. If you do it and you're really strong, maybe you're okay. Do your homework in WebAssign, then go to the personal study plan and take the practice quiz for the section. See how you do on that. And if you need more practice, take it. The biggest mistake calculus students make, especially if they think they're good in math already coming into it, is they don't do enough practice, and that hurts them, and then they have to catch up. All right, I've enjoyed this first lecture. Hopefully it didn't put you to sleep too much, and we'll get on to the next.